June 8, 1943, Henderson Field, Guadalcanal. Lieutenant Commander James Thatch's fingers traced the bullet holes puncturing the captured Mitsubishi G4M's fuselage as tropical heat shimmered off the airstrip's crushed coral surface. The bomber sat where Marine ground crews had towed it 3 days earlier, a relatively intact specimen considering most Betty bombers encountered over the Solomon Islands arrived as flaming meteors or didn't arrive at all. Thatch, the Navy's fighter tactics innovator who had developed the Thatch-Weave defensive maneuver, had flown from Pearl Harbor specifically to examine this aircraft. Captain Marion Carl, the Marine Corps ace with 16 confirmed kills, accompanied him. Both men had shot down Betty bombers. Neither understood why they died so easily. Thatch climbed through the fuselage access hatch and made his way to the wing root section. Standard procedure: check fuel system integrity, assess protection systems, understand why this particular aircraft type had become notorious among American pilots as the flying Zippo lighter. His flashlight beam swept across the fuel tank installation. This cannot be their standard design. No Air Force would build bombers this way. The fuel tanks were completely unprotected. No armor cladding encased them, no self-sealing rubber bladders lined their interiors, no carbon dioxide fire suppression system served them. Just bare aluminum sheet metal, measuring approximately 1.5 millimeters thick, roughly the thickness of a beer can, separated 2,400 gallons of high-octane aviation gasoline from the outside air, and from enemy bullets. Thatch called Carl over. Both men stared in silence. American and British bombers featured self-sealing fuel tanks as standard equipment by 1941. The technology wasn't exotic, a rubber compound layer between the aluminum tank wall and an outer protective layer that swelled when punctured by projectiles, sealing bullet holes before significant fuel loss or fire could occur. The system added weight, approximately 600 to 800 pounds per bomber depending on tank configuration. But it brought crews home alive. The Betty carried none of this. Mathematical analysis would later reveal the implications. 7 separate fuel tanks held 4,380 liters total capacity. The main wing tanks, the largest and most vulnerable, sat exposed in the wing center section, directly in the path of defensive fire from any target the bomber attacked. Tracers, incendiary rounds, or even armor-piercing bullets that struck these tanks would puncture the thin aluminum, atomize the fuel, and create an instant fireball. This wasn't battlefield damage or wartime material shortage. This was original design, deliberate, calculated, approved by Japanese Navy Air Force procurement officers, and built into every G4M from the first production aircraft. The question wasn't whether American intelligence had discovered a flaw. The question was why Japanese engineers had created one intentionally, and what they had gained that justified condemning their own air crews to fly missions in aircraft that offered no margin for error, no second chances, and no hope of survival when hit. The answer lay in the Betty's revolutionary range, and in a design philosophy that would ultimately help lose Japan the Pacific War. The journey to Henderson Field's grim revelation had begun 4 years earlier, in the summer of 1939, when the Imperial Japanese Navy issued Specification 12C for a new land-based attack bomber. The requirements reflected Japan's strategic reality. The Navy needed an aircraft capable of striking targets across the vast Pacific, far beyond the range of carrier-based aircraft, with sufficient payload to sink capital ships. Existing bombers couldn't meet this requirement. The Mitsubishi G4M Nell bomber, then in service, could reach 2,700 miles but carried only 1,760 pounds of ordnance. Insufficient for naval warfare against modern battleships and cruisers. Mitsubishi's design team, led by Chief Engineer Kiro Honjo, faced parameters that seemed mathematically impossible. The Navy specified maximum range of 2,300 statute miles with full combat load, crew of 7, defensive armament of 4 7.7mm machine guns and 1 20mm cannon, maximum speed of 250 miles per hour, and the ability to carry either one 1,760-pound torpedo or 2,200 pounds of bombs. All this from an aircraft that had to operate from land bases using existing runways. The mathematics were brutally simple. Every pound of armor, self-sealing tank material, or protective equipment reduced either range, payload, or both. Honjo's team calculated that equipping the bomber with standard defensive protection systems would reduce range by approximately 40%, cutting the 2,300-mile requirement to perhaps 1,400 miles, unacceptable for Pacific operations. They made their choice. The G4M would sacrifice crew protection entirely to achieve unprecedented range. When the first production G4M1 Model 11 rolled out of Mitsubishi's Nagoya plant in April 1941, the specifications seemed revolutionary. Twin Mitsubishi Kasei 11 14-cylinder radial engines, each producing 1,530 horsepower, drove the bomber to 266 miles per hour maximum speed. Maximum range reached 3,745 miles, nearly twice the combat radius of American B-17 flying fortresses. Internal fuel capacity of 4,380 liters filled 7 separate tanks integrated directly into the wing structure, with no protective systems whatsoever. Empty weight 14,860 pounds. Maximum takeoff weight 20,944 pounds. The Imperial Japanese Navy designated it the Type 1 RICO, land-based attack aircraft. Allied intelligence would later assign it the reporting name Betty. Japanese aircrews would eventually call it something else entirely. The bomber's combat debut came on May 19, 1941, when G4M units from Kanoya Air Group struck targets in southern China. The mission succeeded. No aircraft were lost. The Betty's range allowed it to strike airfields previously considered safe from Japanese attack, while its speed, faster than most fighters then defending China, enabled it to escape interception. But the aircraft's true test came on December 8, 1941, when Japan launched its coordinated offensive across the Pacific and Southeast Asia. At 1:15 a.m. on December 8, 1941, just hours after the Pearl Harbor attack, 27 Mitsubishi G4M Betty bombers from the Kanoya and Mihoro air groups departed their bases in southern Indochina. Their target, the British airfield at Kotabaru, Malaya, where Allied aircraft threatened Japanese invasion convoys approaching the peninsula's eastern coast. The formation flew 400 miles over the Gulf of Thailand in darkness. Navigation lights extinguished, relying entirely on dead reckoning and celestial navigation, the bombers maintained tight formation. At 4 a.m., they began their bombing runs from 10,000 feet. The attack achieved complete surprise. Bombs cratered the runway, destroyed fuel dumps, and caught several British aircraft on the ground. The Bettys turned for home. One aircraft sustained damage from anti-aircraft fire but made it back to base. 26 returned untouched. The real demonstration came 2 days later. December 10, 1941, 1 p.m., approximately 70 miles off the Malayan coast. The British battleship HMS Prince of Wales and battlecruiser HMS Repulse steamed north, searching for Japanese invasion convoys. Admiral Tom Phillips commanded Force Z, Britain's primary naval deterrent in Southeast Asia. Both capital ships had departed Singapore without air cover, believing their anti-aircraft defenses sufficient. At 11 a.m., Japanese reconnaissance aircraft spotted the British ships. By 1 p.m., the first wave of attack aircraft arrived. 8 torpedo-carrying Betty bombers from Kanoya Air Group, followed minutes later by 16 more Bettys from Mihoro Air Group carrying bombs, and then additional waves of torpedo bombers. The attacks developed with precision. The Betty bombers approached at 10,000 feet, drawing anti-aircraft fire, then split into coordinated attack groups. Torpedo-carrying Bettys descended to 200 feet, approaching from multiple directions simultaneously, a tactic called hammer and anvil that forced the British ships to evade toward one threat while exposing their hulls to another. At 1:15 p.m., the first torpedo struck HMS Repulse. The battlecruiser shuddered but maintained speed. 3 minutes later, multiple torpedoes hit Prince of Wales in quick succession, one striking her stern, jamming the rudder and destroying electrical systems. The battleship began listing. Additional Betty waves pressed home attacks. At 1:33 p.m., 4 more torpedoes struck Repulse simultaneously. The battlecruiser capsized within 6 minutes, taking 513 men with her. Prince of Wales absorbed a total of 6 torpedo hits before capsizing at 1:50 p.m., drowning 327 sailors, including Admiral Phillips. The Betty bombers lost 3 aircraft, 1 to anti-aircraft fire, 2 to structural failure during low-altitude maneuvering. But they had accomplished something unprecedented. Land-based bombers had sunk 2 capital ships of a major navy in open ocean. No previous air attack had achieved this. The strategic implications reverberated worldwide. For the Imperial Japanese Navy, the Betty had validated its design philosophy. Range and payload had proven more valuable than defensive protection. The bomber could strike targets no other aircraft could reach, sink targets no other bomber could kill, and do so with acceptable losses. The assumption that losses would remain acceptable would prove catastrophically wrong. Through the first 6 months of 1942, Betty bomber units ranged across the Pacific and Southeast Asia, exploiting their unprecedented operational radius to strike targets Allied planners had considered beyond Japanese reach. They attacked Port Darwin, Australia on February 19, 1942. 54 Betty bombers from Tinian and Rabaul struck the port facilities and destroyed 8 ships. The 1,600-mile round trip from Rabaul exceeded the range of any Allied bomber then operational in the theater. Australian defenses, oriented toward shorter-range threats, couldn't intercept the high-altitude formation. The bombers returned to base with minimal losses. They struck Colombo, Ceylon, on April 5, 1942. 17 Bettys attacking from Mergui, Burma, 400 miles distant, coordinated with carrier-based aircraft to devastate the harbor. The British heavy cruisers HMS Cornwall and HMS Dorsetshire, caught at sea without air cover, absorbed multiple bomb and torpedo hits from Betty formations. Both ships sank within 20 minutes. Only the Betty's range had enabled positioning forces to intercept the cruisers so far from their presumed threat axis. They hammered Port Moresby, New Guinea, throughout March and April 1942. Daily raids by formations of 12 to 18 Betty bombers struck the Allied airfield and port facilities from their bases at Rabaul and Lae, missions that required 800-mile transits over the Owen Stanley Mountains. Allied fighters based at Port Moresby struggled to intercept the high-altitude formations, and the Betty's speed allowed them to outrun most pursuers. Allied air crews facing these raids reported a consistent pattern. The Betty bombers appeared in large formations, flew at high altitude, typically 18,000 to 22,000 feet, maintained tight defensive boxes that concentrated their defensive armament, and executed coordinated bombing runs with devastating accuracy. Their speed and altitude made interception difficult. Their range made them seem omnipresent. American and Australian intelligence officers analyzing these operations recognized they faced a strategic problem. The Betty could strike anywhere within an 1,800-mile radius of Japanese bases. This created an operational bubble covering virtually every Allied position in the Southwest Pacific. Darwin, Port Moresby, Rabaul, the Solomon Islands, even the approaches to northern Australia, all lay within Betty range. The bombers' capabilities forced Allied forces to defend everywhere simultaneously while concentrating nowhere. But the Betty's advantage depended entirely on one critical condition: it had to avoid being hit. Through mid-1942, Japanese tactics and Allied defensive weaknesses had preserved this condition. Betty formations flew above the effective ceiling of most Allied fighters then deployed in theater. When interceptions occurred, the bombers' tight formations and concentrated defensive fire often drove off attackers before serious damage occurred. The few Betty bombers shot down had been destroyed by multiple hits from pursuing fighters, the kind of sustained attack difficult to achieve against high-altitude, high-speed formations. The tactical picture began to change in August 1942, when the United States invaded Guadalcanal and brought modern fighters and aggressive fighter pilots into regular contact with Betty bomber formations at close range. The revelation came quickly and brutally. August 7, 1942, 1:15 p.m., 550 miles northwest of Guadalcanal. 18 Mitsubishi G4M Betty bombers from the 4th Air Group departed Rabaul, Papua New Guinea, bound for the newly captured Allied positions at Guadalcanal. Their mission: strike the invasion fleet supporting Marine landings on the island. The distance, 550 miles each way, lay well within the Betty's operational range. The crews expected standard opposition, scattered anti-aircraft fire, perhaps a few patrol fighters. They were wrong. At 3:10 p.m., as the formation approached Guadalcanal from the northwest at 18,000 feet, Marine Fighter Squadron VMF-223's Grumman F-4F Wildcat fighters climbed to intercept. The squadron commander, Major John L. Smith, had briefed his pilots on new tactics developed specifically for engaging Betty bombers. Ignore the defensive formation, close to point-blank range regardless of return fire, and concentrate all fire on the engines and wing routes, where intelligence suggested fuel tanks were located. At 3:15 p.m., the first Wildcat attack went home. Captain Marion Carl dove through the Japanese formation, his 6.50 caliber machine guns converging on a single Betty bomber. Tracers struck the aircraft's left wing route. The effect was instantaneous. The Betty exploded in midair. Not caught fire, exploded. The entire wing section detonated, sending burning debris across 1,000 feet of sky. The bomber's fuselage tumbled separately, fully engulfed, killing all 7 crew members before anyone could bail out. The fireball was visible from Guadalcanal, 40 miles away. Carl's wingman, Lieutenant Kenneth Frazier, hit a second Betty with a 2-second burst. Same result: instant fireball, immediate destruction, no survivors. The Japanese formation scattered. Marine pilots pursued individual bombers, discovering that any hits to the wing area or fuselage center section produced the same catastrophic result. Betty after Betty ignited, exploded, disintegrated. By 3:45 p.m., the engagement was over. Of 18 Betty bombers that had departed Rabaul, 17 had been shot down. 1, severely damaged, trailing fuel, both engines barely running, limped back to base and crashed on landing. The crew survived. They reported that American fighters had found the Betty's Achilles heel. Marine pilots at Guadalcanal didn't understand what they'd discovered. They reported shooting down poorly protected bombers that burned easily. The pattern repeated itself over subsequent days. August 8th, 8 Bettys attacked Guadalcanal, 6 shot down. August 24th, 15 Bettys struck carrier forces off the Eastern Solomons, 9 shot down. August 25th, 3 Bettys on reconnaissance, all 3 destroyed. Captain Joe Foss, who would eventually become the Marine Corps' leading ace in the Solomons campaign, described the Betty in his combat reports. "It's a flying Zippo lighter. One good burst and they torch up. I've never seen anything burn so fast. Sometimes the crews don't even have time to jump." The nickname spread through Allied fighter squadrons. Flying Lighter, One-Shot Zippo, Flaming Betty. American pilots began actively hunting the bombers, confident that any hits would produce kills. Japanese air crews noticed something else. They were the ones calling in these reports. Their own aircraft had betrayed them. Lieutenant Haruki Iki, a Betty pilot with the 1st Air Group, wrote in his diary after a mission on September 12, 1942, "We call our aircraft Hamaki, cigar, because when hit, we burn from end to end like a lit cigar. Or one-shot lighter, because one bullet is enough. The Americans only need to hit us anywhere near the fuel tanks. We fly every mission knowing we have no second chances." When American intelligence officers at Henderson Field captured the intact Betty on June 5, 1943, forced down by mechanical failure rather than combat damage, they finally understood why. Lieutenant Commander Thatch's examination revealed the technical reality. The Betty's 7 fuel tanks held 4,300 liters total capacity. The main wing tanks occupied the wing's center section, the largest, most vulnerable part of the aircraft and the target of any attacking fighter. These tanks were constructed of aluminum sheet measuring 1.5 millimeters thick. No armor plating protected them, no self-sealing materials lined them, no inert gas system pressurized them. When bullets punctured these tanks, aviation fuel, volatile, high-octane, atomized by the bullet's passage, mixed instantly with oxygen. Any spark, any tracer round, any hot metal fragment ignited this mixture. The result was instantaneous combustion that consumed the entire aircraft within seconds. Thatch compared these findings with American bomber protection systems. The Boeing B-17 Flying Fortress featured self-sealing fuel tanks as standard equipment from 1941 onward. The system used 3 layers: an inner fuel tank wall, a middle layer of vulcanized rubber compounds, and an outer protective layer. When bullets punctured the tank, the rubber layer absorbed fuel, swelled, and sealed the hull, typically within 1 to 2 seconds. The system added approximately 600 pounds to the B-17's empty weight, but reduced fuel-related combat losses by an estimated 60 to 70%. The Betty carried no such system. Thach's report to Naval Intelligence calculated the weight trade-off. Equipping the Betty with self-sealing tanks, armor plating around fuel system components, and a carbon dioxide fire suppression system would add approximately 1,500 to 1,800 pounds to the aircraft's empty weight. With the Betty's existing engine power, this additional weight would reduce maximum range from 3,745 miles to approximately 2,200 miles, a 41% reduction in operational radius. The implications were staggering. Japanese engineers hadn't overlooked crew protection. They had deliberately sacrificed it to achieve the Betty's revolutionary range. The bomber could reach targets 1,800 miles from base, but only by removing every defensive system that might bring its crew home alive. The report concluded, The Mitsubishi G4M represents a calculated design choice prioritizing offensive capability over crew survivability. This design philosophy reflects Japanese strategic doctrine and procurement priorities. American and British bomber design philosophy favors crew protection even at cost of reduced performance. The Betty's vulnerability to defensive fire is not a flaw. It is the intentional price paid for unprecedented range. By late 1943, every Allied fighter pilot in the Pacific Theater knew the Betty's weakness, and Japanese Betty crews flew every mission knowing the same thing. The decision that condemned thousands of Japanese airmen to death in flaming bombers had been made in a Mitsubishi conference room in October 1939, when Kiro Hanjo's design team presented their proposal to Imperial Japanese Navy procurement officers. The Navy's 12-SHE specification, issued August 1939, demanded capabilities no existing bomber could provide. Range, 2,300 statute miles with full combat load. Payload, one 1,760-pound torpedo or 2,200 pounds of bombs. Speed, 250 miles per hour minimum. Crew, 7. Pilot, co-pilot, navigator/bombardier, radio operator, 3 gunners. Defensive armament, sufficient to protect against fighter attack. Service ceiling, 30,000 feet. These requirements reflected Japan's strategic situation. The Navy anticipated war against the United States and Britain across the vast Pacific Ocean. Existing bombers lacked the range to strike American bases in the Philippines, British positions in Southeast Asia, or Allied shipping lanes across the Western Pacific. Carrier-based aircraft, while mobile, couldn't carry sufficient ordnance to sink capital ships, and couldn't operate independently of carrier task forces, which were vulnerable and limited in number. The Navy needed a land-based bomber that could range across the Pacific, strike decisive blows against enemy naval forces, and return to base for follow-up missions. In short, they needed impossibly long range combined with ship-killing payload. And they needed it soon. Kiro Hanjo, Mitsubishi's chief engineer for the project, had designed the G4M Nell bomber, the Betty's predecessor. He understood the physics intimately. He also understood the mathematics were brutally simple. Aircraft range derived from a straightforward equation: fuel capacity divided by fuel consumption multiplied by airspeed. To extend range, a designer could increase fuel capacity, reduce fuel consumption through more efficient engines or reduced drag, or optimize cruise speed. The 12-SHE specification demanded maximum range while maintaining high speed and heavy payload, competing requirements that existed in direct opposition. Hanjo's team calculated the numbers. To achieve 2,300 miles combat radius with 2,200-pound payload required approximately 4,380 liters of fuel capacity. The twin Mitsubishi Kasei engines, then under development, would consume this fuel at roughly 480 liters per hour at cruise settings. At 200 miles per hour cruise speed, this provided approximately 2,000 miles range, close to requirement but with no margin for combat operations, headwinds, or tactical routing. The empty weight budget became the critical constraint. The Navy specified maximum takeoff weight of 20,944 pounds. From this budget, airframe structure approximately 8,500 pounds. Twin engines and propellers, 3,200 pounds. Fuel, 4,380 liters at 6.7 pounds, 7,800 pounds. Crew and defensive armament, 1,400 pounds. Payload, torpedo or bombs, 2,200 pounds. Total, 23,100 pounds, 2,156 pounds over specification. Hanjo faced an impossible choice. Meeting the Navy's range and payload requirements exceeded the maximum takeoff weight by nearly 10%. Something had to be sacrificed. The possibilities: Option 1. Reduce fuel capacity. Cutting 328 liters would save 550 pounds, but reduce range by approximately 350 miles, failing to meet the requirement. Option 2. Reduce payload. Limiting maximum load to 1,500 pounds would save 700 pounds, but preclude carrying standard Japanese torpedoes, defeating the bomber's primary mission. Option 3. Reduce defensive armament and crew protection systems. Contemporary bombers featured self-sealing fuel tanks, approximately 600 pounds, armor plating for crew positions and vital systems, approximately 900 pounds, and fire suppression equipment, approximately 200 pounds. Total weight, 1,700 pounds. The mathematics indicated the only viable path. By eliminating all crew protection systems, Honjo's team could meet the Navy's performance specifications exactly. The aircraft would achieve the required 2,300-mile range, carry full combat payload, maintain required speed, and do so within the weight budget. The justification reflected Japanese military doctrine. Navy strategists envisioned quick, decisive operations across the Pacific. Bombers would strike enemy positions in coordinated attacks, likely achieving surprise and facing limited opposition. The Betty's speed and altitude capabilities would allow it to evade most interceptors. Its range would enable it to strike before enemies could position adequate defenses. And its payload would ensure targets were destroyed in single attacks, minimizing the need for repeated missions against alerted defenses. In this operational context, crew protection seemed less critical than offensive capability. The bomber would succeed through its ability to reach distant targets and destroy them decisively, not through its ability to absorb damage in prolonged fights. Trading survivability for capability appeared rational. Commander Ichiro Yokoyama, the Navy's chief procurement officer for land-based bombers, approved the design in February 1940. His authorization notes, preserved in Japanese naval archives, stated, "The Type 1 Rikko's offensive capabilities justify accepting reduced defensive protection. Strategic employment will minimize exposure to enemy defenses. Range and payload take precedence." Mitsubishi began production in April 1941. The first operational G4M1 Model 11 entered service with Kanoya Air Group in June 1941. Crews received no special warnings about fuel tank vulnerability. Standard operating procedures assumed the bomber's speed and altitude would protect it from sustained fighter attack. For 6 months, this assumption held. Then came Guadalcanal. The massacre at Guadalcanal on August 7, 1942, marked the beginning of systematic Betty losses that would continue throughout the war. The pattern repeated itself across the Pacific theater with relentless consistency. October 11, 1942, 18 Betty bombers from Rabaul attacked Allied shipping at Guadalcanal. Marine F-4F Wildcats intercepted the formation at 15,000 feet. 13 Bettys were shot down before reaching their targets. 2 more crashed on return to Rabaul. 3 survived. 91 Japanese airmen killed, the equivalent of 5 complete bomber squadrons worth of trained crews in a single mission. October 25, 1942, the 1st Air Group dispatched 12 Bettys to strike carrier forces off the Santa Cruz Islands. American F-4F fighters from USS Enterprise intercepted. 9 Bettys destroyed, 2 severely damaged and crashed attempting emergency landings, 1 returned to base. 77 airmen dead. November 12, 1942, 15 Bettys attacked the cruiser force covering Guadalcanal during the naval battle of Guadalcanal. All 15 shot down by combined fighter and anti-aircraft fire. 105 men killed. Not a single torpedo hit achieved. The attack accomplished nothing except adding more names to casualty lists already growing unmanageable. The mathematics of attrition became undeniable. Between August 1942 and February 1943, Japanese Betty bomber units operating from Rabaul against Guadalcanal flew approximately 320 bomber sorties. Allied forces shot down 224 aircraft, a 70% loss rate. Some units ceased to exist as effective fighting formations. The 1st Air Group deployed to Rabaul with 27 operational Bettys in August 1942. By December 1942, only 4 aircraft remained operational. The unit had received 31 replacement aircraft during this period. All but 4 of these had also been destroyed. Total aircrew casualties: 387 killed, 42 wounded. The air group was withdrawn from combat operations in January 1943 and spent 6 months rebuilding. Japanese pilots who survived these operations understood exactly why their losses were so catastrophic. Lieutenant Commander Mitsuo Fuchida, who had led the Pearl Harbor attack and later flew Betty missions, wrote in his memoirs, "We called it 'one shot lighter' because that's what it was. One bullet in the right place and you were dead. Not might be dead, were dead. The fuel tanks would explode, the wing would separate, the aircraft would disintegrate, and you would fall burning into the ocean. There was no time to bail out, no time to fight the fire, no time to do anything except die." The Imperial Japanese Navy attempted to address the vulnerability through design modifications. The G4M2 Model 22, introduced in November 1943, featured a carbon dioxide fire suppression system that injected CO2 into fuel tanks when punctured, theoretically preventing fires. The system added 400 pounds to empty weight, reducing range by approximately 200 miles. It also proved almost completely ineffective in combat. When bullets punctured Betty fuel tanks at combat speeds, fuel atomization and ignition occurred within microseconds, far faster than the CO2 system could react. Marine pilots at Bougainville who encountered the improved G4M2s in December 1943 reported no difference in vulnerability. The bombers still exploded on impact. Japanese crews, recognizing the system's uselessness, often removed it in the field to restore lost performance, choosing to die with slightly better speed and range rather than slightly slower with non-functional protection. The G4M3 Model 34, introduced in January 1945, attempted more comprehensive improvements. Self-sealing fuel tanks in the wing roots, armor plating for crew positions, and modified engine nacelles with improved fire protection. These modifications added 1,800 pounds to empty weight, reducing range to 2,300 miles and maximum speed to 240 miles per hour. Only 60 aircraft were built before production ended, too few to matter and introduced too late to save the thousands already dead. The Betty's vulnerability killed Japanese air power's most valuable asset, experienced air crews. Unlike American forces, which rotated combat veterans to training duties after tour completion, Japanese doctrine kept experienced crews in combat until death or disabling injury. This meant the Betty's losses disproportionately eliminated skilled pilots, navigators, and bombardiers who could have trained replacement crews. The cumulative effect was devastating. By mid-1944, average Betty crew experience had declined from 800-plus flight hours at war's start to approximately 200 hours, creating a death spiral where inexperienced crews flew vulnerable aircraft into combat and died before gaining competence. The most famous Betty loss occurred April 18, 1943, when 2 Betty bombers carrying Admiral Isoroku Yamamoto, architect of Pearl Harbor and commander of the combined fleet, flew from Rabaul to Bougainville for a morale tour. American codebreakers intercepted Japanese communications announcing the visit. 18 P-38 Lightning fighters from Guadalcanal's Henderson Field, led by Major John Mitchell, flew 435 miles to intercept. At 9:34 a.m., the P-38s ambushed Yamamoto's formation over Bougainville. Captain Thomas Lanphier attacked Yamamoto's Betty from below. His 4.50 caliber machine guns and single 20mm cannon raking the bomber's wing root and fuselage. The Betty's unprotected fuel tanks ignited instantly. The aircraft crashed into the jungle, killing all aboard. Japan's most capable naval strategist died because the bomber carrying him exploded from a 3-second burst of gunfire. Late in the war, desperate Japanese planners found one final use for the vulnerable Betty: kamikaze carrier. The MXY-7 Oka rocket-powered suicide bomb, essentially a piloted missile with a 2,650-pound warhead, couldn't take off under its own power. Betty bombers carried Oka bombs underneath, releasing them within range of American ships. The tactic proved suicidal for both Oka pilots and Betty crews. American fighters targeted the slow, heavily laden Betty carriers long before they reached release range. On March 21, 1945, 16 Betty bombers carrying Oka bombs attacked Task Force 58 off Kyushu. Navy F-6F Hellcat fighters intercepted the formation. All 16 Bettys were shot down before releasing their Oka bombs. 112 men died. 7-man Betty crews plus Oka pilots without achieving a single hit on American vessels. The final toll remained uncounted until years after war's end. Between April 1941 and August 1945, Mitsubishi produced 2,435 G4M Betty bombers across multiple variants. Production breakdown by model. G4M1 Model 11, initial production, 1,200 aircraft, April 1941, October 1943. Twin Mitsubishi Kasei 11 engines, 1,530 horsepower each. Maximum speed, 266 miles per hour. Range, 3,745 miles. No crew protection systems. G4M2 Model 22, improved version. 1,154 aircraft, November 1943, March 1945. Twin Kasei 21 engines, 1,825 horsepower each. Maximum speed, 272 miles per hour. Range, 3,265 miles. Carbon dioxide fire suppression system, largely ineffective. Slightly improved defensive armament. G4M3 Model 34, final version. 60 aircraft, January-August 1945. Twin Kasei 25 engines, 1,825 horsepower each. Maximum speed, 240 miles per hour. Range, 2,300 miles. Self-sealing fuel tanks and limited armor protection. Too little, too late. G4M2E Oka carrier variant. 21 aircraft modified from G4M2 airframes, March-August 1945. Modified to carry MXY-7 Oka suicide bombs. All 21 destroyed in combat operations. Of 2,435 aircraft produced, Japanese records indicate approximately 1,847 were destroyed in combat operations, a 76% loss rate. An additional 312 were destroyed in non-combat accidents, many involving fuel system fires during training or transit. Only 276 Betty bombers survived to war's end, with most subsequently scrapped. Aircrew casualties proved harder to quantify. Japanese military records, often incomplete or destroyed, suggested approximately 15,000 aircrew positions were filled over the Betty's operational life. Given a 7-man crew and estimated loss rates, between 8,000 to 9,000 Japanese airmen likely died aboard Betty bombers, making it among the deadliest aircraft in history for its own crews. Survivors' accounts painted a consistent picture. Petty Officer Takeo Tanimizu, who flew 47 Betty missions before being reassigned to training duties in May 1944, wrote post-war, "Every mission was Russian roulette. If you flew enough times, you were going to be hit. And when you were hit, you were going to die. Not injured, die. I watched 23 crews burn. You couldn't rescue them, you couldn't help them. You just watched them fall. After 47 missions, I was one of 3 surviving members from my original squadron of 27 crews. The Betty killed more Japanese than it killed Americans." For comparison, the Boeing B-17 Flying Fortress, the American bomber closest to the Betty in mission profile, featured comprehensive crew protection from initial design. Self-sealing fuel tanks reduced fuel fire casualties by approximately 60 to 70%. Armor plating protected crew positions and vital systems. Redundant flight controls allowed continued flight after bottle damage. Multiple self-sealing fuel tanks compartmentalized fire risk. The weight penalty was substantial. A fully equipped B-17G carried approximately 2,300 pounds of armor plating, self-sealing tank materials, and protection systems. This reduced the B-17's range to approximately 2,000 miles with combat load, roughly 1,700 miles less than the Betty's maximum range. But it brought crews home alive. American records indicated that approximately 60% of B-17s damaged by enemy fire returned to base successfully. Crew survival rates for aircraft shot down exceeded 50%. Most crews could bail out before catastrophic structural failure. Between 1942 and 1945, the B-17's crew survivability allowed the United States to maintain experienced bomber formations despite heavy combat operations. Pilots completed 25 mission tours, rotated to training commands, and passed their experience to replacement crews. The system created a virtuous cycle where veteran knowledge improved survival and survival preserved experience. The Betty created the opposite cycle. Its vulnerability meant crews rarely survived being shot down, no time to bail out when the aircraft exploded. Its lack of protection meant even minor damage often proved fatal. And Japanese doctrine's refusal to rotate combat veterans meant experienced crews stayed in combat until killed. By 1944, the average Betty crew had dramatically less experience than their 1942 predecessors, flew more vulnerable missions as Allied defenses strengthened, and died in greater numbers. The philosophical difference between American and Japanese approaches revealed itself most clearly in procurement priorities. When presented with the range versus protection trade-off, American military planners consistently chose protection. The reasoning was straightforward. An aircraft that brought its crew home could fly again tomorrow. An aircraft that burned on first hit could fly exactly once. Over extended campaigns, survivability proved more valuable than maximum performance. Japanese planners chose differently. They prioritized offensive capability, the ability to strike distant targets decisively over crew protection. The reasoning reflected cultural and strategic assumptions. Decisive early victories would win wars before attrition mattered. Individual sacrifice for mission accomplishment was expected and honorable. Japan's limited industrial capacity meant maximizing each aircraft's striking power mattered more than preserving crews for prolonged conflict. This philosophy succeeded brilliantly for 6 months. From December 1941 through May 1942, the Betty's revolutionary range enabled Japanese forces to strike targets across the Pacific, sink British battleships, devastate Allied airfields, and establish the defensive perimeter that Japanese strategy required. The bomber performed exactly as designed. Then came attrition warfare against an enemy with greater industrial capacity, better crew protection systems, and superior replacement training pipelines. The same design choice that had enabled Japan's early victories, trading survivability for range, became the mechanism of defeat. Each mission cost irreplaceable crews. Each loss made the next mission more dangerous for less experienced replacements. The Betty had been designed for a short, decisive war. It faced a long, attritional one instead. By August 1945, surviving Betty units were training for suicide missions. There was no longer any pretense that crews might return. June 8, 1943. Henderson Field, Guadalcanal. Lieutenant Commander James Thatch completed his examination of the captured Betty bomber and prepared his intelligence report. The technical findings were unambiguous. The design philosophy they revealed was unmistakable. 2 years and 2 months later, on August 19, 1945, a Mitsubishi G4M Betty bomber, painted white with green crosses to indicate surrender delegation status, departed from Kyushu carrying Japanese envoys to meet American occupation forces at Ii-Shima. The aircraft that had opened Japan's Pacific offensive would now formally end it. The irony was complete. The Betty that had sunk HMS Prince of Wales and HMS Repulse, that had ranged across thousands of miles, striking targets no other bomber could reach, that had pioneered naval aviation tactics and demonstrated the vulnerability of surface ships to air attack. This revolutionary aircraft would be remembered primarily for killing its own crews in horrifying numbers. But the lesson wasn't simply about poor engineering. The Betty was brilliantly engineered to achieve specific goals. Those goals simply didn't include bringing Japanese aircrews home alive. And in that single fact lay the entire story of why Japan lost the Pacific War. The Betty represented design philosophy as strategic doctrine. Japanese planners, facing an enemy with superior industrial capacity and resources, believed decisive early victories could force favorable peace terms before American war production reached full capacity. This required weapons optimized for maximum offensive capability, even at catastrophic cost to crew survivability. Range mattered more than protection. Striking power mattered more than sustainability. Mission accomplishment mattered more than individual survival. American planners, confident in their industrial superiority and committed to extended operations, designed weapons for sustainable attrition campaigns. Protection systems reduced immediate capability, but enabled repeated missions by preserving experienced crews. The B-17 sacrificed 1,700 miles of range compared to the Betty, but its crews flew 25 mission tours, rotated to training commands, and passed their skills to replacements. American bomber effectiveness increased throughout the war as experience accumulated. Japanese bomber effectiveness collapsed as experience burned. The mathematics were unforgiving. The Betty's unprotected design killed approximately 8,000 to 9,000 Japanese airmen over 4 years. These casualties represented not just lost individuals, but lost expertise. Pilots who had trained for years, navigators who understood celestial navigation over trackless ocean, bombardiers who could execute precision attacks. Each loss removed knowledge that couldn't be replaced at wartime training rates. By 1944, replacement Betty crews averaged 200 flight hours versus 800-plus hours for their 1941 predecessors. They died faster, accomplished less, and taught nothing to the next generation because few survived long enough to accumulate teachable experience. The strategic calculation that seemed rational in 1939, trade survivability for tapeability, proved catastrophic in the attritional war that actually occurred. Japan's limited industrial capacity meant each aircraft lost represented a greater proportional loss than American equivalents. Japan's limited pilot training capacity meant each crew killed created irreplaceable expertise gaps. And Japan's cultural resistance to defensive fighting meant these losses were accepted as inevitable rather than addressed through design changes until far too late. Modern military procurement still grapples with these trade-offs. Stealth aircraft sacrifice payload and range for survivability through reduced detectability. Armored vehicles sacrifice mobility for crew protection. Fighter aircraft balance maneuverability against weapons capacity. Every design reflects assumptions about acceptable risk, expected operational environment, and the value placed on bringing operators home alive. The Betty stands as history's clearest example of what happens when these calculations prove wrong. It achieved revolutionary capability through revolutionary sacrifice, and the sacrifice proved unsustainable. The examination of the captured Betty at Henderson Field provided final proof. The Mitsubishi G4M was not poorly designed. It was brilliantly designed to achieve specific goals within specific constraints, by engineers who solved an impossible problem through radical compromise. Those goals simply required accepting that thousands of Japanese airmen would die in instant fireballs when Allied bullets found their mark. And when Lieutenant Commander James Thach's fingers traced those bullet holes through paper-thin aluminum into unprotected fuel tanks, he understood exactly what he was seeing: the physical manifestation of strategic philosophy. A design choice that valued mission over crew. A calculated decision that offensive capability justified defensive vulnerability. An engineering solution that prioritized what the bomber could destroy over whether its crews would survive. The Betty bomber proved that revolutionary weapons sometimes require revolutionary sacrifices. And it proved that the most dangerous design decisions aren't those that fail outright, but those that succeed brilliantly, until the war they were designed for transforms into the war that actually happens, and the sacrifices accepted as reasonable become unsustainable, and the calculations that seemed rational reveal themselves as fatal. The burned wreckage scattered across every Pacific battlefield told the same story. Design philosophy reveals national strategy more clearly than propaganda or doctrine ever can. And when design philosophy accepts crew death as necessary cost for mission capability, it writes the epitaph not just for the crews, but for the strategy itself.